Hello, everyone. Hope you're doing well. We are continuing to wrap up our review week this week, especially when it comes to things that are introducing logic, sets, and functions for this class, as these are going to be kind of the basic building blocks of what we're going to see as we move forward through some more complicated topics later on. Now, I wanted to go ahead and make a quick divergence here because for several reasons. One reason is this. One thing that is a common theme in this sort of world of analysis is that we are only rigorous for the sake of trying to be aware of any counterexamples that might exist to some of our theorems. For example, you might remember if you've seen this before in history of math, that Isaac Newton, when creating the derivative, just came up with some sort of variable that is non-zero, but its square is zero. We know that some sort of variable like that cannot exist with our current axioms of the real numbers. And so a lot of people in the 19th century were like, well, what am I supposed to do with this? How am I supposed to go farther with this notion of a derivative that uses some sort of made up terminology that I'm just supposed to believe for a second in order to define this thing? And that is where Cauchy came up with the idea of, well, let's go ahead and define this derivative using something called a limit. And that's where we got this sort of notion. And notice that once we define something rigorously, once we delve deeper into the notions of what was happening at the level of mathematics that it wanted us to be at rigorous-wise, that we were able to now start blossoming this world a little bit. We weren't able to we could just take a derivative maybe if we had some sort of differential value that is non-zero, but that square is equal to zero. You can define a derivative with that sort of thing and make some sort of processes out of that. But you can't really go much farther because you're kind of building something on top of a fabrication. You can maybe do it for a specific purpose, but you're not able to build upon that because you're like, okay, well, what things work and what things don't anymore. It becomes a little bit uncertain about how to move forward. Countability is one of those places that is helpful in helping us see some very interesting and unique counterexamples. A lot of what we're going to be talking about today is due to a mathematician known as Georg Cantor. And Cantor was excommunicated from his church for the time for the things that he was developing, or maybe a similar kind of trope as you may remember that Copernicus, for saying that the Earth revolves around the sun, saw a similar treatment, and other kinds of people who've kind of seen this sort of pattern throughout the years. The main point being that there was a notion of a norm, and then there was something that came across that challenged that norm. And it was uncertain at first about how we go about and react to that. And a lot of what we're doing in today's class, in this class this semester, is getting used to some things that battle against the norm, the things that we think about. What we'll see today are some examples of sets and functions that challenge the norm of what we think are sets and functions. And that's exactly why we're talking about countability. We want to be rigorous in our mathematics, and this is intuition as to why, because there are a really strange examples of things out there that challenge our notion of what sets and functions are supposed to look like. We'll see some examples as we go through today. But we're also getting a little bit of something that will be continuing through a theme of our class, is this notion of different types of infinity. There are many different parts of mathematics that we'll go through and explore in this class, some of which want you to only have something be true for countably many sets or uncountably many. So we'll go through and be rigorous about what we mean for those definitions. Countably infinite and uncountably infinite are now going to look very different for us. So we'll talk a little bit about this in this section today. Where this all stems from is what we are probably the best at manipulating and working with, which is things that are finite. And we'll start there to say that a set has cardinality n if it contains exactly n elements. We would then say that such a set is finite. So something like this would be a finite set. If it had a cardinality of n, then that means that it has exactly n elements, and that is going to be a finite set. What this is doing is it's kind of saying, okay, you're getting a relative size of this set. You're counting how many elements are in it, and that number of elements is n. The reason that we give this term is that there are other cardinalities out there, not just those of finite values, but we could say a set A has cardinality aleph null, spelling out what I'm saying here. I'm saying aleph, this is the Hebrew letter, aleph, and null. And this is because NULL is kind of what sometimes you would hear for this 0 down here. You might hear aleph naught as well, the kind of the same sort of thing. And rarely do you hear aleph 0 is the reason that I kind of spell this out, is that this is cardinality, typically is said as aleph null or aleph naught, or the countably infinite cardinal. So this is the countable if it is possible to make a list out of the elements that you have. So we will say that it is possible to make a list out of these elements like A1, A2, and in particular, if that thing is an infinite list, then we would say that this sort of thing is countable. So 1, 2, 3, 4, you can make those into a list, so the natural numbers are a countable set. Now notice here that I'm actually including inside of this the notion of finite sets. Actually, finite sets are themselves countable. Any set with cardinality n is going to be countable because you can make them into a list. There's no rule in this list making that I'm saying is that you can't just repeat elements. So A1, A2, dot, 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 AN, and once you get to that nth element, you can just repeat that element over and over and over again. That's a way to write a finite set as in a list. So if we want to be specific about countable, to say that it is an infinite list that we're working with, and we will say that the set is countably infinite. So we'll say countably infinite if it is an infinite set that is also countable. So an infinite, go ahead and write that here, an infinite countable set will be called countably infinite. And this is some sort of terminology that we might see here in the future. This is kind of in contrast to something which is not countable, which would be uncountable. Now, I could go through and say uncountably infinite if I would like, but there's no real need for that distinction. All uncountable sets are going to be infinite because we know that the finite sets are themselves countable. So any set which is not countable is uncountable. Let's start. We've gotten some examples here of countable sets. Let's start taking a look at our first uncountable set. You may have seen some examples of things that are countable versus uncountable. Let's get an example here of an uncountable set. Let's consider the set known as the power set of n. Here, the way I'm going to write this is with a little script P, and then put whatever I'm taking the power set of on the inside. So for example, if I'm looking at the power set of the set from 1 to 2, and then the way that I might write this is I'm going to take the set of all subsets of the set 1, 2. So the empty set is itself a subset, as is the set containing 1 and the set containing 2. Finally, the entire set is a subset of itself, so we would include that as one of these sets inside of the power set. Notice that there's a little bit of a relationship between the cardinality of the set that I'm plugging in, which is 2, and the cardinality that I'm plugging in, which is 4. Some of you who have seen a little bit of combinatorics here might be able to figure out how many elements are in the power set from 1, 2, and 3 after going through and doing this. The combinatorial argument is this. For every subset of the set 1, 2, and 3, you either are going to include 1 or you're not going to include 1. You're either going to include 2 or you're not going to include 2, or you're going to include 3 or you're not going to include 3. Those 3 choices have to be made. Each choice gives you 2 options. And remember and note that each option that you choose at each stage is going to give you a different subset. So we should expect 2 times 2 times 2 elements inside of this space. 2 times 2 times 2. Each 2 is coming from the fact that we have to include or not include any element in here inside of each of our sets. So we should expect to see 8 elements in the power set here. And we can go through and check to see what we end up getting there. We should get the empty set, 1, 2, and 3. Then we should get the sets with 2 elements in them, 1, 2, 1, 3, and 2, 3. And then finally, the set containing all of our elements, 1, 2, and 3. We should expect to see 8 elements out of that. Notice that this is 2 to the 3, where n, this value n is going to be the cardinality of our original set. To get the cardinality of the power set, you're taking it to be 2 to the n. For that reason, you will sometimes see the power set written in the following way. You will see this as the power set of n is 2 to the n. And that's saying you're taking the set of all values of n and saying for the subsets of n, I'm going to say I'm going to either include that set or I'm not going to include that set. Notice that you can get infinite collections inside of the natural numbers, even if you're not including all of the natural numbers. For example, there is an infinite proper subset of n. An example might be the even numbers. So the even numbers can be put into a list. You can list them out and say that, well, maybe say, to be specific, the positive even numbers, since we might want to do that. So we can put those into a list of 2, 4, 6, 8, so on and so forth. Those are very listable, and they're infinite as well. So you have a countably infinite subset of the natural numbers. So some of these subsets inside of the power set are things like the even numbers. They could be infinite, but they don't even have to follow a pattern. You could just be picking at random whatever numbers you want to include in any given subset. It does not have to be something that follows a very specific rule. It could just be, oh, I'm going to include some numbers, or I'm not going to include some other numbers. So the power set of n has a lot of elements in it. And that is why we're going to see that this has some intuition as to being uncountable, is that we are taking a countable set and choosing whether or not to include each and every element, giving us 2 to the countably infinite number of values in that sort of set. And that's something interesting to us. So this sort of exponentiation, this calculus that goes along with the ordinals is somewhat rigorous. It's a little bit strange, right? You could say probably that 2 times Aleph null is equal to Aleph null. And the reason for this is if I take 2 sets that are of the same size and count all of them all together, so Aleph null plus Aleph null, if you will, then counting all of those should still give us something that's countably infinite, because I should be able to just count along the way. One from the first in the list of the first set, and then the first in the list of the second set, and then just keep going second and second, third and third, fourth and fourth for each of those elements in that list. And I should be able to combine those 2 lists into one. What we want to show for the power set is that 2 to the n, or 2 to the Aleph null, does not have that same sort of listability, that this is something that's going to be too big for us to work with. And the proof of this is Cantor's theorem, which is what Georg Cantor, this is the same namesake of this person. So let's say that first, that the power set of the natural numbers is countable. The first words in this proof are if it were, and that is using the beginning of a proof by contradiction. So we're supposing by way of contradiction that the power set of the natural numbers is countable. Makes sense in this context because we have a pretty solid definition of countability. Countability says that you can put things into a list, whereas uncountable just means you can't put them into a list. So why not assume you can put things into a list and then show that that list is absurd, so that the only other option that you have is to show that there was no such list for the power set of the natural numbers. So if this is a countable collection, then we can list each and every element inside of the power set of n as subsets. Note that these A1, A2, these are all subsets of n. So we'll keep that in mind as we kind of go through and do this. And that's going to be important because we're going to be looking at the elements of these A sub i's that are inside of this list. Now, we're assuming that A1 through A2 to A3, all the way in that list, that contains every single subset of that natural numbers as part of our contradiction proof. So let's go through and now construct a set that should be somewhere inside of this list. Here's how I'm going to construct that set. I'm going to take the element S, or this element of the power set of the natural numbers. And I'm going to make it all of the values, k in the natural numbers, such that that element is not inside of A sub k. So notice I'm saying this element of k is not within the set that has its own number as its own index. So for example, let's say that somewhere in this list, I get that A1 is 1, 3, and I get that A2 is just a set of odd numbers. So A1, so then we can ask about S given this listing. S would then be equal to, would it have 1 in it? No, it would not have 1 in it because 1 is an element in A1. Would 2 be in it? Well, 2 would be in the set S because 2 is not in the set A2, which is the set of odd numbers. So we would start our set by putting the number 2 in there. And then we can keep going all the way down whatever list that we created. We can't actually say this is a 1 and this is a 2. That would be putting some sort of supposition on what our list is. So we can't actually say 2 is in whatever the set is. It depends on the list that we create, going from A1 to off to infinity. So this set S is of the type that it does not contain, it's of the set of all indices of our sets that do not contain those indices inside of those sets. So this is going to eventually get you a subset of the power set of the natural numbers. So S itself needs to be somewhere in this list, because we said that you could list out all of the power set of the natural numbers and get every single subset. Since S is a subset of the natural numbers, this has to be somewhere in this list. Let's call that element n. Let's say that S is in this list somewhere, and let's say that it is a sub n. So here, again, notice that I'm not actually presupposing what this index is. I'm just saying, let's say it's somewhere in this list, and let's say it's a sub n. Now let's ask an interesting question. This question is going to reveal the absurdity of what we have just done. This subset, which is the set of all indices such that the sets do not contain the indices, is going to result in something that is absurd. Let's see if we can find what that is. Is n inside of S? Notice that this n here, this value n, is exactly the index that we're saying the set S appears in our list, A1, A2, A3. So that's the n that's being referred to here. Well, let's start by saying that it is. If n is inside of S, then n is such that n is not in A sub n. That's what it means to be inside of the set S, is that n cannot be in that particular element. But note that we said A sub n is equal to S. So if we answer yes to the question n is in S, we end up with something absurd, which is that n is not in S. So well, that cannot be true. So this must mean that n is actually not in S, because we saw that n was in S led to a contradiction. Now, is n not in S? Let's go through and talk about what that means. If n is not in S, well, then that means it is not the case that n is in A sub n. That's because if n is not in S, that must mean it did not make this requirement. Well, the only way you do not make this requirement is if that value n is inside of the set A sub n. So actually, that means that n is in S, because again, A sub n is in S. So again, since it is not the case that n is in A sub n, this must mean that n is in A sub n is equal to S. It's not the case that it's not in A sub n, so it must be in A sub n. But that's another contradiction. So either direction that we could go, since every element is either in or not inside of a set, gives us a contradiction. The only assumption that we ended up needing to make was that the subsets of n were actually listable, that you could get them to be countable. So this must be the thing that was not true in our argument. This is the absurdity that we found was just by constructing this set S, which ended up not being very nice at all. It's so not nice that we found out that no matter what your list is, it cannot be put into a list. That tells us that this list that we formed did not include all of our subsets, no matter how we formed our list, so it cannot be listable. And that gives us the fact that the power set of n is uncountable by definition. We define the power set of n to have the cardinality aleph 1. Aleph 1 here is the cardinality of the power set of the natural numbers. So another way that we will sometimes write that is 2 to the aleph null, or a 2 to the n, or however else you might write that. Notice now that you could use this argument one more time to say, okay, does the power set of it, if the power set of n has aleph null, is it true that the power set of the power set of n has that same cardinality? Excuse me. Well, think about it this way. Now we are taking, instead of the natural numbers as the things inside of our sets, A1, A2, A3, we are now taking in the power set of the natural numbers. The elements of our sets are subsets of the natural numbers. So those are the things that we are attempting to list. But this same sort of argument is going to tell us that taking another power set augments our cardinality one more uncountable ordinal step. That means that that's actually not going to be equal to the same type of cardinality as what we had before. There's a way to say that we cannot actually write it out in this sort of way. That is a way to say that the cardinalities The number of uncountable cardinalities is actually infinite, that you can go as far as you can go. Taking the cardinality of the power set of the natural numbers gives us a new uncountable ordinal, a new form of uncountability, which we call Aleph 2. So Aleph null is the only countable ordinal, whereas everything after that is something that is uncountable. Aleph 1, Aleph 2, so on and so forth. If we continue doing this, we see that there's actually infinitely many levels of uncountable sets. And this is kind of a little beautiful thing, but inside of the infinites discussion behind mathematics is how can we understand these sorts of levels of infinity? The idea that we're saying here is that the way that you are gauging that these two infinites are not the same is you're doing this. We can say that we can say two sets A and B have the same cardinality if there exists a bijection between the two sets. That is, F goes from A to B. So for example, when we say that you can list the natural numbers, what we're doing is we're saying you can make a bijection between the natural numbers and itself. In fact, for any other countable set, you can list them. Well, what is that? That is actually bijection between that set and the natural numbers. You're saying that the number 1 goes to the first element in that list. We were calling it on the previous screen A sub 1. Then 2 becomes A sub 2, 3 gets mapped to A sub 3, and so on. So countable sets are those that have the same cardinality, or there exists a bijection between with that set and the natural numbers. So using this sort of argument, we could go through and say that the power set of the natural numbers and the power set of the power set of the natural numbers do not have the same cardinality. We could just keep going through this. So countable means that there exists a bijection between that set and the natural numbers. So that's a new definition for us, and sometimes a needed perspective. We can then define a set as countable if it is in bijection with n. That is, that there exists a bijective function g that takes us from the natural numbers to that set. So that would be a notion of countability. In fact, notice here that countable actually includes the finite, so I need to actually change this a little bit more. I need to just say, instead of it being bijective, it really just needs to be surjective. That is, that every element inside of the set A is getting covered by some sort of natural number. It's possible that two things get mapped to one, as otherwise A would have to be an infinite set. I couldn't get a bijection between an infinite and a finite set. So notice the kind of change that has to happen there. So you have a surjective with the natural numbers. So really, instead of bijection here, I should be saying it is surjection. If there exists a surjection, I'll have to just kind of rewrite a little bit of it now just to make sure that it looks all right. But that's how that goes sometimes. So if there is a surjective function, that looks like this. So a surjective function g going from the natural numbers to that set A. So that tells us how we can start comparing some of these sizes together. Same cardinality, meaning there's a bijection between the two sets, and things like this. There is a theorem known as let me get the names on this one right. I believe the names are Cantor, Schroeder, and Bernstein on this theorem. These three names together have come with the theorem, and it's kind of attributed to some of these and not all of these, depending on how you kind of see it, which is that there is an actual order on cardinalities once you do this. That is, that you can always say if there is an injection and a surjection between any two sets. If there exists an injection and another function that is a surjection, then you can always construct a bijection. That's something that maybe we don't think about, is that, well, if you have an injection and another surjection, surely you could always form a bijection. But that's something that requires a proof, and it turns out to be a little bit complicated. But it ends up being true, which means that this notion of greater cardinalities and lesser cardinalities in terms of injections and surjections now makes a little bit more sense. So we can say which ones are greater and lesser in terms of injections and surjections as well. So there's a whole science now to this world of cardinality. We can talk about all of these sorts of things. And there's a lot of further along math that deals with exactly these types of uncountability. Now, here's a set that might surprise us to see that it is countable, the set of positive rational numbers. This is a countable set. It's certainly bigger than the natural numbers because the natural numbers are included inside of this set. They are positive rational, but it's still countable. So taking a set larger than the natural numbers still allows us to get a bijection. Remember that that bijection can also be thought of as just a list of those numbers, and I have constructed a little proof idea here. This is one of those proof by pictures or proof without words. Do you ever see these at some point? Maybe you've seen this for the Pythagorean theorem. Now, oftentimes these theorems they tout themselves as proofs without words, but oftentimes they're also unclear about where they're trying to go towards. So allow me to take this idea and make it clear what I'm attempting to express with this sort of theorem. First thing I can do to see if the set of positive rational numbers is countable is I can take the numbers, natural numbers up on top and the natural numbers down on the bottom, and I can make a table of those numbers in the following way. I can say the column attributes the numerator of a number, and that the row number attributes the denominator of a number given at that point. So something in the third column, first row, would be 3/1. Something in the first column, third row, would be 1/3. So that tells us about how we could be getting elements inside of this table. Now, that's not something listable yet because I've only gone through and drawn a table of things at that point. But notice that we do end up getting all of the rational numbers this way, at least the positive ones. We're starting with a positive number up on top, can't be zero, can't be negative, and then a positive number down in the denominator. And so by our definition of rational numbers, these are all of the positive rational numbers. Okay, so then how are we going to make a list out of this? You may have noticed the little red arrows that I have already drawn on this picture. That's how I am constructing my list. The table starts at a specific spot. It starts in the top left, and I'll make that my first element. Then I will go across and to the right to make my second element of my list. I will then proceed diagonally, going down and to the left to find my third element. So the path that I've been taking has been 1, 2, 3. At that point, I'm done with that diagonal, so I will continue stretching down to get to the next element in the list that I'm going to make, and that's going to give me my fourth element. Because there is room now to go top and to the right diagonally, I'm going to go ahead and take that as far as I can take it. Now, you may have noticed that at this point, I have repeated a value. I've repeated the value 1/1 because that's really just the value 2/2. But remember, we said at the very beginning, it's okay if we end up repeating values. That's okay in terms of a list. So that is something that is fine for us. If we were very adamant about creating a bijection, then we could say, let's create this list so that we're skipping over any duplicate values. That's something that we could go through and define rigorously if needed. But for now, we are just listing all of these values, and that's good enough for us. We have gone through and kind of described how we're going to do this process, and so we just keep repeating it, and we notice that if we continue this process all the way through the table, then we're eventually going to get to reach to everything. We're going to eventually get to every single element inside of this table as we continue this list. So what's happening here? We are taking our list to just be the set of all of these kind of diagonal traversals that we're taking through this table. If we go from 1 to 2 to 3 to 4 to 5 to 6 is labeled here, and just keep that pattern going, we're going to list out all of the elements inside of the positive rational numbers. And that's exactly the definition of countable. So that's where our proof without words is here in this particular setting. Now, let's go through and talk a little bit more about some things that have us going through and doing countability, because this sort of proposition is interesting to us. It turns out that a countable union of countable sets is itself countable. One way to kind of consider this is that you could think of a countable union of countable sets as some way as if it is indexing the elements of that set by countable indices, the number of sets that you have. So let's say, for example, you have A1, A2, A3, so on and so forth. Each of these are countable sets. Well, if these are all countable sets, then you can go through and list each of them. Maybe you list each of them in a row. And if you do that, then for each A1, A2, and A3, you can list all of the elements of A1, A2, and A3 in a different row. Since you have countably many things, you can eventually get through the entire table of everything you're listing down this way. Now the lists go this way and the lists go this way, but you have the table set up as you had from before. Try putting some of those pieces together here and try and do this proof as a little bit of an exercise to talk about how you can use that table that we said from the previous proposition to prove that a countable union of countable sets is itself countable. Another corollary of this is that the natural numbers, the integers, and the rational numbers, not just the positive rational numbers, are all countable sets. The way to think of the rational numbers, for example, here is to kind of help us to use a little bit of our bijection tool as well. Well, first, if the positive rational numbers are countable, if these are countable, well, then the negative rational numbers should be countable, because I can think of a bijection that exists between these two things. If you have a value p over q and you'd like to map it over somewhere to something in the negative rational numbers, if p over q is positive, then negative p over q is negative. And that should be a bijection between the two sets. Excuse me again. Notice that this is a well-defined function, which we'll talk a little bit more about well-defined functions in a bit, because that is important. Well-defined function, because if I have two elements over here that are the same, let's say that I have another r over s, that is equal to p over q, because there's more than one right way for me to write an element inside of this domain, then that's still going to map to the exact same thing over here. Negative p over q is equal to negative r over s. The reason that we say well-defined here is that we say a function is a function f is well-defined if every element in the domain maps to exactly one element in the codomain. So technically, we should not be able to call something a function if it's not well-defined. So this is merely just kind of emphasizing the notion of what we're saying is a function. So in fact, if we wanted to be very rigorous about this, what we might say is we might say that f is actually a mapping, and then say that this is a well-defined function. If. So emphasizing well-defined here means that it actually does map. It does the function definition that we want it to. That is, that every element of the domain maps to exactly one element in the codomain. So the reason for being specific here is what happens if we're looking at the positive numbers and we have 1/2 and 2/4. Well, now I have to be sure that because these two elements are the same in my domain, that they map to the same place in my codomain. If they map to two different places, well, that's one point going to two different places. This would not be a well-defined function at that point. So that's the reason behind this specificity. This is a well-defined bijection between the positive rationals and the negative rationals, because if I have two fractions over here that are equal, they map to two fractions that are equal in the codomain. Notice, as an example of something that is not well-defined, if I had gone through and said, let's take a bijection between the positive rationals and the natural numbers, let's take p over q and map it to the value of the numerator, something like this. This would be not well-defined. This one's not well-defined because there are multiple ways that I could write the number 1/2 that changes the value in the numerator. So the question is, what does 1/2 get mapped to? Does it get mapped to 1? Does it get mapped to 2? Does it get mapped to 3? Technically, by our assignment, it's getting mapped to all of these things. So this is not a well-defined function. Okay, so this is an example of something that is not well-defined, because 1/2 gets mapped to 1, 2, 3, and in fact to every natural number with this as sort of assignment. Going back to our original thing before the tangent, the rational numbers being countable, we've shown that the positive rational numbers are countable and that there exists a bijection with the negative rational numbers. So that's a countable set. Finally, we know that the set containing 0 is countable. So the rational numbers being the union of a countable set, a countable set, and a countable set, all told give us something that is countable. We can do a similar thing as to show why the integers are a countable set, given that the natural numbers are a countable set. So these countable unions of countable sets are all countable. Here's a proof that n squared is countable. Again, this is n times n in terms of the Cartesian coordinates. So this is all of the elements m and n being natural numbers. Then you can notice that if I fix an n in the second coordinate and then allow that first coordinate to just kind of run, then I get a countable set. That's m comma n for all m inside of the natural numbers. Here I'm fixing n. So each individual n that I fix gives me a countable set, and there's going to be countably many of those sets to go through in union. So the union over all of these second coordinates I could be fixing of these sets where I allow the first coordinate to run gives us all of n squared. And this is a good enough proof that n squared is countable thanks to our previous proposition. So then we can reference our above proposition. And then we're done. So a lot of sets are countable. Things like the natural numbers, integers, rational numbers, n squared, so on and so forth. It seems right now that the only things that are uncountable are things that we have to take subsets of. Things like power sets of the natural numbers. We could go through a similar argument to see the power set of the integers is uncountable. Power set of the rational numbers is uncountable, so on and so forth. In fact, these should all have the same cardinality as the power set of the natural numbers, since the natural numbers and the rationals can be replaced back and forth since they have the same size. So there is a glaring kind of omission here, which is I see natural numbers, integers, rational numbers. I see the Cartesian products of any sizes of any of these sets. What about the real numbers? This is something that maybe you have seen before, which is that the real numbers are not countable. And there's a different type of table proof that we can use to show this. Now, the issue here at this stage of where we're at, I referenced this back in a previous video, is that the real numbers are a little bit tricky for us to define right now. We don't have all of the machinery to define the real numbers in a way that is satisfactory to us. So we're going to have to use a slightly sketchy definition, which is the set of all infinite decimal expansions. The reason that something like this might be a little bit sketchy is that you have things like this happening, 0.999 repeating. You may have seen an argument about this, but this number is actually can be referenced as an infinite series, that this is 9/10 plus 9 over 100 plus 9 over 1,000, and so on and so forth. So if I have 0.999 repeating, that's going to be an infinite series, because what I'm doing is an infinite decimal expansion. Really, that's just an infinite sum of the kind of partial decimal expansions. We don't have anything in the world that is just that is an infinite decimal expansions by itself. It's always a limit of terminating decimal expansions. And the way we can get those decimal expansions is just by taking cuts like these over here. Those correspond exactly to the partial sums of this infinite series here. Well, what is the limit of this partial series? Well, we have that this is 9 times 1 over 10 to the n. Notice here we're starting as n goes from 1 to infinity here. And we can use our geometric series to write out what this is going to be. Well, this is 9 times the value of, what is it, 1 over 1 minus 1/10 minus 1. That minus 1 coming from same as before. This minus 1 is saying I'm not going to be including 1 inside of this sum. So this is 9 times this, so we should get 9 times 10/9 minus 1. So this is actually what? When I go through and calculate this, this is 9 times 1/9. This is the value of 1. So the issue with infinite decimal expansions is that you get certain numbers to look the same, even if they're not written in the same way. So 0.999 repeating gives us 1, for example. Well, you could imagine this happens with any repeating decimal expansion with a bunch of 9s. That you could always get it to just be, okay, 0.000, and so on and so forth. This is one of those things that like you'd have to go through and talk about a little bit when you write these things down. So set of all infinite decimal expansions results in some numbers being equal, even if they're not written in the same way. Kind of like how rational numbers can be written in a similar sort of format. You might be familiar with the way that we could be dealing with this, something called an equivalence relation, forming a partition of the real numbers. We'll talk about equivalence relations later on in this class when it becomes a little bit more handy, especially when we start talking about constructing the real numbers. So let's run with this definition for now, a set of all infinite decimal expansions, and let's see where it takes us. We're going to need a lemma for this proposition now that we've given a perspective on the real numbers that we can use, the set of all infinite decimal expansions. And that lemma is this: any subset of a countable set is also countable. This is hopefully something that, at least intuitively, is not that hard to grasp. If I take a collection or even a subcollection of a countable set, well, that subcollection should not be in greater cardinality than the set that it came from. The way we're going to use it is as a corollary of the countable union of countable sets is countable. And then we're just going to make our sets something that's either the empty set or the set containing each and every individual element inside of our countable set. This is, of course, countable. Its greatest cardinality is 1. It could be 0. And this is a countable union. A countable union of countable sets is countable. So this gives us a good proof of this lemma, and we'll just kind of move on from that. We'll use the contrapositive of this lemma at the very end of our proof, namely that if you take an uncountable set, then what? There's going to be some subset that is also uncountable. All right. Or rather, it's the opposite. If you have a countable set, then the subset is countable. Any countable set, uncountable set, and in a larger set, that larger set has to also be uncountable. There we go. Found out what that was, had to reparse it a little bit. So maybe to help us out together, any set S containing an uncountable subset R is itself uncountable. That should give us the contrapositive of this lemma. I like having all of this extra space on the screen to be writing stuff. You might look back on these notes and be like, look at all this extra space John didn't use. But sometimes it comes in very handy to have that whole screen just be able to say, oh, I'm writing some stuff up on top here and over to the side here, so on and so forth. So let's take a look at this proof now that the real numbers is uncountable. And let's see if we can see how this gets around some of the sketchy stuff with 0.999 equaling 1. So here is the theorem. That is that the cardinality of the natural numbers is strictly less than the cardinality of the real numbers. We first assume, by way of contradiction, that the numbers in the open interval from 0 to 1 can be listed. So this is what we're going to show is uncountable, and that's where this lemma is going to come into play. If you have an uncountable subset of the real numbers, then the real numbers has to be uncountable. So we can prove this theorem by just showing the open set from 0 to 1 is uncountable, and that's exactly what we're going to do. Because now, when we start forming a table that contains the listed real numbers going from 0 to 1, then I can list it as if they start from 0 point and then keep going all the way down. We know I don't have to include 1 point somewhere because I'm not including 1 in my set. So here is that list. We have, that's the way that this list would be formed is something like this: 0 point, maybe I just have 1, 2, 3, 4, 0.2159, 0.3, I'll use a different number than 1 there, 3, 4, 3, 9, something like this. And the way that I'm going to work with this list is, let's assume that this list gets us through all of the real numbers. Then I'm going to do a similar thing to Cantor's theorem, which is try and find something that does not work in this list. No matter how I form the list, it's not going to work. So the way I'm going to do it is I'm going to start by taking a look at all of the diagonal entries in this list, kind of looking along these lines. And the way I'm going to go around this is I'm going to create a number, which is going to be either the decimal point there is either 1 or 2, whichever that diagonal entry is not. So I'm going to take this list. Here's the first element, the second element, the third element. And I'm going to create a new number. That new number, in my case, is going to be like 0.2, 2, 1, so on and so forth. That rule is saying if I have a 1 in one spot, let's go ahead and replace it with a 2. If I have a 2 in that spot, then let's go ahead and replace it with a 1. If it's neither, then I could choose either 1 or 2. I could have chosen this number, or I could have chosen 0.222, because the number given here is neither of those two things. But I'll go ahead and say maybe it defaults to 1 unless the number is 1, in which case then I'll go ahead and call it 2. So, question, where is this new number inside of the list? Well, it can't be equal to the first element because the first element differs from the new number in the 10th position. And if they differ in the 10th position, then unless I have like a repeating sequence of 9s all the way through here, then I'm not going to be able to actually say that that's what this is. Well, let's think through that spot, right? Well, notice that the only way that you could get 0.1999 to equal any number that starts with 0.2 is if it's equal to 0.2. This is by a similar argument to what we did on the previous slide. But take a look at the next decimal in our new number. It's not 0.20, it's just 0.2 that we would get from this sequence of 9s. So because the next number is not a 0, we're not going to get any overlap in that sort of set. So the way that we've constructed this number allows us to get far away even from those repeating decimal expansions that actually become other expansions. So 0.1999 can only equal 0.2 with zeros on the other side. So that cannot be our new number either. Now, this also cannot be our second number. So if I take a look at the second number in the second decimal position, it's also a different number. 1 is different from 2, so these two cannot be the same number. This number is different from the new number in the third position, so the third number in our list cannot be this new number. But we can repeat this argument the entire way down the entire list. The new number that I have constructed cannot be the nth number because it differs from it in the nth position. It is different from it in the nth decimal place. But since k that we formed is a real number, k is not in our list. So 0, 1 cannot be listed because we found, kind of like in the Cantor's theorem, something that could not be formed as a part of our list. So by our lemma, our real numbers is uncountable. All right. So this is this sort of structured proof, as maybe you've seen before, but with this little added thing of how do you deal with the fact that some non-terminating decimals can look like other decimals. It turns out that the way those decimals work, though, is not exactly as we are getting around that with our way of constructing this number here by just saying k sub I is either 1 or 2. If we had said that it could be 0, then we might actually get some repeating numbers. If we say it could be anything, we could get something that actually is in our list, just written in a different way. Okay. So these are some of the strange things that we see here with the notion of infinity with these things. Now, I've been talking a lot already and having a good time with it, and it's because uncountability is very exciting to me. But I haven't even gotten to some of the meat and bones of what we're kind of getting to with this stuff, because now that we have uncountable sets like the real numbers, then what can we do with these uncountable things? Can we form sets and functions out of these that are not quite intuitive in how they work? And so we're going to take a look at something called the Cantor set as one of these examples. We will see the Cantor set come up with some of our problems and some of the things we look toward in the future. And here's how we define the Cantor set. The draw behind this set before we talk about it is that it's going to be an uncountable set as well, as a subset of the real numbers, but it's not going to contain an interval. Now, think about other sets that do not contain intervals, like the natural numbers and the rational numbers. None of these sets contain an interval. In fact, any interval that you might contain, if it goes from A to B, then we can do a similar argument as what we did in the previous slide and show that this is actually an uncountable set. So by our lemma, once again, it must be the case that sets like the natural numbers and the rational numbers, these contain no intervals. That is, you cannot say that a subset of these numbers is an interval. So the rational numbers contains no intervals, and this kind of makes sense. You might have heard the notion every interval contains an irrational number. Here's a good reason as to how you prove that. If it were all rational numbers, then that subset would be uncountable, and hence the rational numbers would be uncountable, which would be a contradiction with our understanding that positive rational numbers are countable, and hence going back through our theorems that we've talked about from before. But what's interesting is that this is not a characterization of countability, because you might ask a question. Are all sets containing no intervals countable? You might ask yourself this question because the natural numbers, the rational numbers are countable, and the open interval from A to B is uncountable by our previous proposition. So are all sets containing no intervals countable? Is this one way to go through and make this connection? And this Cantor set is going to be a counterexample to that. It's going to answer no, and its counterexample is going to be exactly the Cantor set. So let's go through and define what this is. Let's consider the interval going from 0 to 1, and let's define that to be C0. So I start with this set right here. The next thing I'm going to do is form a set C1 by taking out the middle third of any interval that's remaining inside of that set. So take a look at this set, for example. The middle third is going from 1/3 to 2/3 for this interval. I'm going to go ahead and take that out. That's no longer a part of this interval. So if I wanted to write out what this is, that this is the closed interval from 0 to 1/3 union with the closed interval from 2/3 to 1. Now I have this set, and I'm calling this one C1. Notice I now have two intervals instead of the one. I've kind of done a little bit of that saw in half trick. Now for C2, I'm going to repeat the process of what I've done from before. There's an inductive process going on here. Now for the set C sub k, given any interval remaining in the set C sub k, I'm going to take out the middle third. In C sub 1, for example, there are two intervals. For each of those intervals, I'm going to take out the middle third. The middle third in this first interval is 1/9 to 2/9. So I'm going to go ahead and take that out and leave the rest. 0 to 1/9 union with 2/9 to 1. I will do the same thing for the second interval in C1. I'm going to cut that one into thirds. That is the 7/9 to 8/9 interval. So I'll cut that one out and just get left with these four intervals to go along with. Notice that C2 now has four intervals. C3 has 8 intervals, and notice that the lengths of each of these intervals are getting shorter and shorter. The length of intervals can be gotten by a formula. C0 is 1, C1 is 1/3, C2 has intervals of length 1/9, C3 has an interval of length 1/3 to the third, and in general, C sub n is going to have a length of an interval 1/3 to the n. The way we define the Cantor set is the intersection, the elements that are inside every single one of these sets. This is called the Cantor set. It's the intersection of all of these sets. So if any one point that is taken, any one point that is taken out of any of these middle thirds is no longer in the Cantor set. If it's out at one step, it's out forever. All right, so this is the intersection between each of those sets, and that's how we're defining the Cantor set. Is the Cantor set empty? Is a good question. Are there any elements inside of all of these sets altogether? There are. Zero's in there because 0 is an endpoint of one of those intervals, and so it's never going to be the middle third. In fact, now we can get that as a kind of a pattern. Any endpoint of any of these intervals is going to be in the Cantor set because it can never be the middle third of an interval. It's always at the end. So if you get to any step and take a look at the endpoints, you can always include those together. So for example, you have 2 endpoints at C0, you have 4 endpoints in C1, 8 endpoints in C2, 16 endpoints in C3, and you might actually see now that there is a little bit of an intuitive notion as to why this set is not only non-empty, but also uncountable. Take a look at our patterns between our numbers. When we get to C sub n, we're going to get to not only infinitely many endpoints, but the way that we're getting there is very similar to how we could be counting the power set of the natural numbers. This is going to be 2 to the natural numbers many endpoints once I go through and look at the intersection of everything. So counting all of these endpoints together should give us something like this. This can be an intuition to us as to why this is actually an uncountable set. Is that this is 2 to the natural numbers. Now, I'm not going to allow this as a rigorous argument, but instead just as an intuitive one that kind of allows us to see that maybe there's some sort of bijection going on between this and the power numbers, or the power set of the natural numbers here. So there's some sort of connection happening here. There's like a choice that's going on. Now, something I would allow you to do is take a bijection between the power set of the natural numbers and these endpoints, if you would like. But what we haven't gone through is said, well, what about everything that's not an endpoint? Anything that's not an endpoint of an interval eventually is going to be in the inside of the interval, and hence will eventually be in the middle third. That's some sort of the argument that still needs to be dealt with this notion. So let's actually do a proposition where we classify exactly the points inside of the Cantor set. And that's what this proposition is all about. It says, let's say an element C is inside of the element C. Well, then I can actually look at that element C and say it has to be written in a specific way. The way that it's written is that it is of the form, the sum goes from n goes to 1 to infinity of a sub n over 3 to the n, where a sub n is either 0 or 2. If it can be written in this form, then it can be written with respect to this infinite sum. So this proposition is saying, okay, I can actually clarify what each of these kinds of these values look like. So notice, for example, the way that we're expressing 1/3, since we said that was an endpoint here, is as this infinite sum, which is n goes from 1 to infinity of, and I'll actually write it out as a sum here. This will be a little bit more useful, as 0/3 plus 2/9 plus 2 over 27 plus 2 over 81 plus ... so on and so forth. This is one way to write the number 1/3. And by the same sort of argument as we've been using in the previous slides, this kind of gives us a little bit of a quasi-infinite decimal expansion, this time in terms of thirds instead of in terms of tenths. You go through and calculate what this is going to give you in the geometric series, that should give you 1/3. So that's going to be inside of the Cantor set because I can write this in terms of this one sum. Well, how are we going to do this? We're going to use our endpoint idea to help us out. We proceed by induction. Since C is inside of C1, C is either in the interval 0 to 1/3 or 2/3 to 1. Note that every element in 0 to 1/3 is less than 1/3. So if C is equal to this sum, then A1 is equal to 0. Similarly, every element in the latter interval, 2/3 to 1, is greater than or equal to 2/3. So A1 equals 2, unless perhaps C equals 1. The dealing with 1/3 and 1 is similar to how we had to deal with it up here. So this part right here, this other slide that we're talking about, is that we're just going to deal with it in this sort of infinite repeating decimal expansion sort of way. So now, assuming that A1 through AK are inside from 0 to 2, we know that C is inside of C sub k plus 1 by our definition of being in the Cantor set, which is that it is inside of the intersection of each of these C sub n's. So C is either in the interval, and we just express what it means to be inside of C sub k plus 1, which means that it's inside either one of the intervals that were left after cutting out the middle third. Well, the way that you would go through and write that is you would have either a sub k plus 1 being 0 or being 2. The fringe cases at the endpoints that it's talking about can be dealt with the exact same way as how we dealt with 1/3. If you have maybe something is 2/3 plus 1/9, then you could be dealing with 1/9 in a way that has it as infinite decimal expansion. And using geometric series, you can rewrite it in that sort of way. Induction hypothesis is going to complete the proof. To explain a little bit more about what I mean by these fringe cases, you might benefit from reading through this slide where I explain a little bit more what I've been trying to hint toward with these little bits of hints here and there. So it's hard to get a handle on now how the set C might actually look. All we can do is imagine that these points are somehow at the endpoints of each of these intervals. So if I'm asked, okay, I'm going to take the Cantor set and I'm going to actually draw it on our number line, then how is it supposed to look? Well, if this is 0 and this is 1, then I know that these guys are going to be in there, and I know that these guys are going to be in there, and I know that these guys, which are in the middle thirds, are going to be in there. And it seems like there's a lot of concentration between specific points. Well, there's a neat way to visualize the Cantor set using something called the Cantor function. What's interesting here first is that we have already seen this proposition, that C contains no intervals and yet is uncountable. We've seen the no intervals part. We haven't quite gotten to the uncountable part, although maybe we could start taking a look at that, the bijection between this and the power set of the natural numbers by the selections between 0 and 2 that we're going to make. We're going to do it in a slightly different way. We're going to form a bijection between the Cantor set and the interval going from 0 to 1. So here's what we're going to do. We're going to define a function going from the Cantor set to the interval 0 to 1, and we're going to claim that that function is surjective. Now, what is that going to mean? If it's surjective, that means you have to have at least as many elements inside of the Cantor set as you do in the closed interval from 0 to 1. But because the closed interval from 0 to 1 is already uncountable, the Cantor set C is itself uncountable. Incredible. Let's see if we can find what this bijection is. Note, by the way, that the Cantor set is literally just a collection of points, and we're about to put it into bijection with something that is entirely an integral. We're about to set a bijection between something that has no intervals in it at all and something that is entirely one integral. And here's how we're going to do it. Remember that we said that we could take any element inside of the Cantor set and write it as a sub n over 3 to the n, this infinite sum, where a sub n is either 0 or 2. So using this assignment, let's take any element inside of the Cantor set, which can be written in this form, and let's map it to the following point. Notice some of the subtle changes that are going to happen in this place that I'm mapping it to. Where I am mapping it to is the element a sub n over 2. So this one is either 0 or 1 because the a sub n is either 0 or 2, and I'm just dividing by 2. And then instead of having it be divided by 3 to the n, I'm going to be dividing it by 2 to the n. Notice the subtlety here. 0 and 2 gives us basically 2 out of the 3 options inside of a ternary expansion of a number. Here, ternary expansion means if I get something into base 3, then the only numbers I have available are 0, 1, and 2. So I could think of the number 1/3 as equal to 0.0222 in base 3, repeating, of course. I could think of 7/9 as, in fact, I'll do a different number. I'd like to do 8/9. I could do 8/9 as 0.2. This is saying that this is 2/3 plus, and then I could put a 2 right here to say that this is equal to 2/9. And then I could do zeros all the way out to be, this is in base 3. So notice the difference between something like this and something in just a general expansion. 0.1234 is instead saying that this is 1/10 plus 2 100ths plus 3 1,000ths plus, and so on and so forth. This is the addition of those numbers. Whereas a ternary expansion is adding the things in terms of instead of tenths, hundredths, and thousands, it's thirds, ninths, 27ths, 81sts, so on and so forth. So this is how we're getting these sorts of numbers. But now that we've boiled down things into 0 and 1s, we're now not in ternary expansions, we're in a world of binary expansions. This binary expansions is going to be looking at 0.10110001, numbers of this form, where everything here is given in terms of base 2. The first decimal point is 1 times a half plus 0 times 1/4 for the next position, plus 1 times 1/8 plus 1 times 1/16. Skip a few places, plus 1 times 1 over 128. That is the binary decimal expansion of one of these numbers. Notice, by the way, that this is a surjective function because you could have just set the a sub n's to be any collections of 0s and 2s. Those are all inside of the Cantor set, which means that these numbers in the numerator of the fraction that you end up with could be any combination of 0s and 1s. So that's all possible combinations of 0s and 1s and getting all possible binary expansions. So you can even say here, let's say, for example, that you write some arbitrary element x in 0 and 1. Then you can write it in terms of its binary expansion. Then you can say exactly what element gets mapped to that point. It's the a sub n over 3 sub n, where here a sub n is equal to 2 times the b sub n that you were using to define the binary expansion of an arbitrary element inside of 0 to 1. So C has at least as many elements as 0 and 1 does, but because 0, 1 isn't because 0 and 1 is uncountable, C is therefore an uncountable set. An incredible argument. It says that the Cantor set has no intervals and yet is an uncountable thing. The idea is that the endpoints continue to coagulate the more and more that you get them as you continue to go down the way, and you get something that looks a lot like the power set of the natural numbers. There's one last step that I want to take us here, which is in the notion of something called the Cantor function. This is that weird function that I was telling you about a bit before, which is going to take exactly this argument, and it's going to riff off of this a little bit. Now, notice that we have been able to map the Cantor function to the interval from 0 to 1, but we can make an extension of this slightly. If we extend the function f defined in the proof above to be constant in the gaps between the points of the Cantor set, then what we get is the Cantor function from the interval from 0 to 1 to 0, 1. Here is how that function is formed. We start by looking at elements that are not inside of the Cantor set, and we say, okay, let's go to the very leftmost point in that gap. So maybe we start from going from 1/3 to 2/3. That's a gap inside of the Cantor set. Well, then we look at 1/3, the leftmost point, and we say, okay, where is that point getting mapped to? in the Cantor set, or in the Cantor function? Well, 1/3 is 0/3 plus 2/9 plus 2/27 plus ... Where is this getting mapped to? In our function from above, this is getting mapped to 0/2 plus 1/4 plus 1/8 plus so on and so forth all the way down. I'll give one more term for sake of constancy. There we go. Because we're changing 3 squared, 3 cubed to 2 squared, 2 cubed, and we are dividing each of those numbers by 2 as we go through and do that. Well, this is an infinite sum, and we can calculate what that is. That is equal to 1/2. So where does 1/3 get sent to in the assignment that we gave up above? It goes to 1/2. Then we define the Cantor function inside of this gap to just be a constant until the Cantor function picks back up. We then repeat this process for every single other gap. You can think here's 1/9 and 2/9. And 1/9, if you send 1/9 through the assignment from the proof above, that's going to send you to 1/4. If you send 7/9 through this gap, you're going to get sent to 3/4. And so you're just making the function constant through that gap. And then we continue this process all the way through. Once we've done that, we put the Cantor function back in with respect to what this function actually is defined to be. And once you get that, you have the entire Cantor function, which looks like this. Here is something called the devil's staircase. This is another way that this is sometimes said. Devil's staircase is a beloved term, if you would, for this sort of function. Because what's happening here is that you might notice that every single place here, except in the Cantor set, is completely constant. The Cantor set contains no intervals, and yet this function is completely constant on every other spot outside of this collection of intervals. But yet, even though it's completely constant on each of those intervals, it still is able to climb from 0 to 1. Devilry, some might say, and that's the idea behind this devil's staircase, is that how can it be that these no interval sets can allow us to climb through this particular function? I noticed that I've included both pictures here. The right picture is good for several reasons. One, it tells us how we are forming the Cantor set to begin with, but it also gives us a better picture in some respects of what the Cantor function is. There's no interval of consistent increase in the Cantor function. Even though it looks like you have little parts like right in here and here and here, where it looks like the function is just consistently increasing, it's not. If you zoom in, you're just getting constant intervals again, all the way through. There is no one place where it is consistently increasing. So the picture on the right shows you what's kind of going on. We're just filling in more and more constant parts. And once you get through all of that, you end up getting to this thing called the Cantor function. And we'll study this function a little bit as we go throughout this course. Now, I wanted to not leave us without an exercise in this. So I've included it here at the very top of this slide, and I'll write it down here at the bottom what my solution for this is going to be. The exercise is this. Let's show that the sequence of all rational numbers, R sub n going from 1 to infinity, is a countable set. So this is not connected to this function here. So if you need to take some time to take a look at that, that's totally fine. We aren't going to use this function to prove this exercise, but instead, I want to show a little bit about what we would be trying to do in terms of working through these exercises. The set of all sequences of rational numbers is countable. Some of you may already have an idea about this. Well, let's consider what the sequence of all rational numbers is. You're starting with a rational number here. So rational number, so on and so forth, all the way down, and you're continuing this process in a list. Now, these are sequences of rational numbers, so I know that the rational numbers themselves are countable. Is there a way that I could use one of the theorems that we've talked about from today to say that this set is countable? Well, let's see if something like that is possible. Here's how I'm going to try and do it. I'm going to define Q1. Let's do it like this. Let's say just Q1, and I'm not going to use the bolded font. I'm just going to use Q1 to be the set of all sequences of the form Q, 0, 0, so on and so forth. In fact, I'll write Q1 here. And then I'll write Q2 to be the set of all rational functions that are Q1, Q2, 0, all the way down. And here, what I'm doing is I'm saying everything except the first n elements inside of this set Qn are going to be 0. Q1 through Qn. Notice that these can absolutely be 0 if they want to be, Q1 through Qn, namely, but they don't have to be. What I am saying has to be is anything past the nth element. Well, notice that there is a bijection between Q1 and Q. There's a bijection here, and how do you do it? You're just mapping Q1 to Q1. So this element is going to get mapped to just the element Q1. Notice that there is a bijection between Q sub 2 and Q, the rational numbers, squared. And what you're doing is you're mapping this to the Cartesian coordinate Q1, comma Q2. This is a bijection between each of these sets. Similarly, I can get a bijection between Q sub n and Q to the power of n in a very similar way. I'll leave some of the details here for you, but what I'm trying to say is that if you now consider the set of all these rational numbers, maybe I'll just call this set Q when I go through and write it, is that Q is the union as n goes from, through the natural numbers of Q sub n. In fact, Q sub 2 contains Q sub 1, but that's not really the important part here. What I'm saying is that this countable union of countably many sets is itself countable. So I'm using that theorem here. So if I take this fact plus countable union of countably many sets is countable, then I should be good to go. So consider this a proof idea. I've shown what a full proof might look like in some of the previous exercises, and I've shown you the full depth of proofs that I expect in some of the other kinds of slides here. So hopefully this is enough for you to start trying to piece together what this proof should look like. So try finishing this proof. Try making it to a sense that it's rigorous enough that it matches a lot of what we've been doing in the proofs that are up above here. But putting all of this together gives us that the rational numbers are going to be countable, or at least rather not that, just that, but the sequences of rational numbers. A way that we will sometimes write this set is as Q to the power of infinity. This is the sequences, because you're kind of thinking of this as like, yeah, you are taking finite sequences and looking at their limit, so going off toward infinity for this. So we will use notation like Q to the infinity to say the set of sequences of rational numbers. We could do a similar thing for n infinity, r infinity, and so on and so forth, that these are sets of sequences. These are sets of sequences where the elements inside of those sets of sequences are natural numbers, rational numbers, or real numbers, respectively. But that'll do it for us today. We've gone through a good bit here with countability and the different types of infinity. I hope you didn't mind if I took my time. I really enjoy this sort of stuff, and I wanted it to be very clear what I was saying as we went through it. It's, a lot of these things are indeed kind of, they take our intuition for a trip, let's just say it, put it that way. So we've gone through and talked about Cantor's theorem to show that the power sets form a whole list of uncountable ordinals. We've shown the calculus behind countable sets, how to show some sets are uncountable, and how that can be used to define things like the Cantor set and the Cantor function. But that'll do it for me today. Thank you so much. Have a wonderful day.